Back again. In this video, we're going to talk about capture velocity in a local exhaust ventilation system. Capture velocity is the velocity of air movement required to draw in the contaminant that we're trying to collect. Again, with local exhaust, we're using the system to suck out the bad contaminants. And you got to have enough capture velocity to suck out those contaminants in your work area. It's a function of flow rate in the system, the cross-sectional area of the ductwork, how big the ducts are, and the distance between the inlet or the hood, again using those terms interchangeably, and the contaminant source. This is the formula that you are very likely to see on the CSP exam. This is a capture velocity formula. Just take a quick look at this. Again, V is our capture velocity. That's the suction that we're going for, the level of suction to suck out the bad stuff. Q is your volumetric flow rate in cubic feet per minute. 10 is a constant. X is the distance between the inlet and the contaminant that we are trying to collect. And then A is the cross-sectional area of the duct in square feet. But I do need to say a little bit more about this formula. This is an ASP-CSP formula, and I really question its utility in real-world ventilation settings. If you're really working with a ventilation system, it's limited in its use. It only applies to hoods that don't have a flange. Remember, we talked about flanged hoods and unflanged hoods. Most hoods are going to be flanged because flanged is more efficient for collecting the contaminant. But this formula really only applies to hoods without a flange. It also only applies if the capture distance is 1.5 diameters or less. So if we're working with a 6-inch duct, this is only going to be accurate out to 9 inches. 1.5 diameters, 6-inch duct, we're talking about a 9-inch distance. There are other formulas that would be more appropriate if you're really involved in designing ventilation systems or testing ventilation systems. But this is the formula that you need to be familiar with on the CSP exam. Again, very common to have problems requiring test takers to use this formula. Another note, well, I already mentioned this. It's a repeat of the note we have here. It's only accurate with distances less than 1.5 diameters. It's not accurate if the capture distance is greater than 1.5 diameters. Also want to mention what we mean by cross-sectional area. We've talked about that in a previous video and some previous calculations, but let me go ahead and get it squared away, make sure we know what we mean by cross-sectional area. It's the two-dimensional area of a three-dimensional object when the three-dimensional object is intersected by a plane. It's a slice or a cross-section, the area of that slice or that cross-section, whether it's round duct like we have here or square duct. Cross-sectional area is also used when in other applications as well. It's not just a concept that's used in ventilation calculations. Cross-sectional area is an engineering concept used in a lot of different types of applications. Now, for our purposes, you could just think of the cross-sectional area as the area of an opening or the end of our ductwork. You know, what is the area at the end of our ductwork or the opening of our ductwork? All right, well, let's go ahead and take a look at some problems like you might see on a certification exam. But before I do that, getting a little ahead of myself, let's talk a little bit more about capture velocities. Capture velocity is affected by the type of contaminant that we're working with, the type of material being captured. In this table below here, we have the recommended capture velocities for different contaminants. And you'll notice the different contaminants are are categorized by what we're calling the energy of dispersion. Low, average, high, or very high. Energy of dispersion is the amount of energy it takes to get the material moving. If it's a lightweight material, a fine dust or a mist, it doesn't take a lot of energy to get that material moving. With that kind of low energy of dispersion material, it's only going to require a low capture velocity. If we're dealing with heavier dusts or gravel or grit from a grinding disc that has a higher energy of dispersion, then we're going to need a higher capture velocity to efficiently capture that type of contaminant. All right, well, let's go ahead and take a look at the kind of problem that you might see on a certification exam. We have a non-flanged hood which has a round opening and a diameter of 6 inches. The hood has been designed to have a volumetric flow rate of 800 cubic feet per minute. The hood is used to remove contaminant vapors 6 inches away from the opening. What is the required velocity to capture this contaminant? Again, here's our formula for calculating the required capture velocity. Now, this note over here, if the flow rate was not known, we may have to calculate that flow rate before we can use this formula to calculate our capture velocity. But in our example here, the flow rate is known. It's 800 cubic feet per minute. So we're good to go. Everything we need is here except for our cross-sectional area. We're going to have to calculate that cross-sectional area. And here is our calculation of that cross-sectional area. Again, we're talking about circular duct. The area of a circle is pi r squared. That's the formula that we're going to be using. Pi is 3.14. We'll just round it to 3.14 for our purposes here. Now, the only wrinkle in this is that we're given our diameter in inches and it needs to be feet. So 6 inches is 0.5 feet. So our diameter is 0.5 feet. But the formula is asking for a radius. So 0.5 feet diameter, we need to divide that by 2 to get a radius. Radius is 1/2 the diameter. So the radius is 0.25 feet. And that's it. The rest of us just doing the multiplication. Now we first have to square 0.25, which gives us 0.0625. Multiply that times 3.14 that we're using to represent pi. And our area is 0.196 square feet, our cross-sectional area. Now we have everything we need to plug into the formula and do the calculations, to finish up the calculations. So let's go ahead and do that. Our flow rate is 800. Again, 10 is a constant. Our distance is 6 inches away from the opening. That's the distance between the contaminant and the inlet that we're working with. We also need to convert that 6 inches to feet. 6 inches is 0.5 feet. That's X. And then we plug in the area that we just calculated. We do these calculations. We do the calculations in the denominator, 10 times 0.5 squared plus 0.196. We end up with 2.696. Now we want to divide 800 by 2.696, and there's the capture velocity that we need to effectively capture this contaminant. 296.7 feet per minute is the capture velocity we need. All right, let's do another problem that's a little more involved. Actually, this one's not that much more involved, but we're using a rectangular duct instead of a round duct. Remember, round is generally considered more efficient, but there will be systems where square duct is used. We have a rectangular hood, and again, there's no hood really. It's just the raw opening of the duct. There's no flange. Rectangular hood has an opening of 4 inches by 6 inches. The volumetric flow rate in the system is 725 cubic feet per minute. What is the capture velocity required to remove the contaminant at a distance of 7 inches? Again, it's 7 inches from the source of the contaminant to the inlet. Same approach as before, as the previous problem. We start with our formula. Our cross-sectional area calculation is a little bit different. It's a little more straightforward. The area of a rectangle is simply height times width. We do need to convert 4 inches to feet, and we need to convert 6 inches to feet. 4 divided by 12 is 0.33, so we're talking about 0.33 feet times 0.5 feet. We end up with a cross-sectional area of 0.165 square feet. Now we can start plugging things in. Again, flow rate, 725. 10's a constant. 7 divided by 12 is 0.58. That's the distance. Remember, x is the distance between the hood and the source. So 0.58 feet is the equivalent of 7 inches. Again, don't let that throw you up on the exam. Make sure you're doing everything in feet for these types of calculations. That goes cross-sectional area, and the distance between the hood and the source needs to be in feet. But in the problems, it'll normally be given to you in inches. So again, don't let that throw you up. Then we plug in our area that we calculated, 0.165. Do our calculations in the denominator, 10 times 0.58 squared plus 0.165, end up with 3.529. Now we divide 725 by 3.529. We end up with a capture velocity in this situation of 205.4 feet per minute. To capture this contaminant, we need to have our capture velocity at 205.4 feet per minute. All right, do another one. This one is probably more along the lines of what you'll see on the CSP exam than the other two that we've looked at. The other two have kind of led us up to this particular problem, and some of the other videos that we've looked at and some of the concepts covered in those videos also play into this as well. But let's just dive in. The 6-inch branch duct is providing exhaust flow to capture and remove a contaminant. What is the required capture velocity if the capture inlet is 5 inches from the hood? Okay, here's our formula. We need flow rate, but it's not giving us flow rate. It does give us this diagram, and it tells us to focus on the 6-inch branch. So there's what we're working on, the 6-inch section right here. Go ahead and mark the rest of this out. We don't need that. Okay, we're only on this 6-inch branch duct. We're going to have to calculate the flow rate, and we can do that using this formula. Flow rate equals cross-sectional area times velocity, but we're going to have to calculate the area and the velocity in this 6-inch branch. First of all, calculating velocity. Here's the simple formula for velocity, but we need to calculate velocity pressure first. To find velocity pressure, we use the total pressure formula and the information that's given to us in the diagram. We have static pressure and total pressure. We plug those into the total pressure formula, and we solve for velocity pressure. We add 3 to both sides. Our velocity pressure is 2. Now we can take this velocity pressure back over to this formula and calculate our velocity. Again, 2 for velocity pressure. The square root of 2 is 1.41. Multiply that by the 4005 constant. Our velocity is 5,647.05 feet per minute. We also need area of the duct. And it's a 6-inch branch duct. It's round. We're using the formula for area of a circle, pi times r squared. We need to do it in feet. So 6 inches becomes 0.5 foot diameter, but we need the radius. So radius is 1/2 the diameter, so it's 0.25 feet is a radius. Once we have it plugged in, we square the radius, multiply by the 3.1416 that we're using for pi, and there is our cross-sectional area. Now we have the cross-sectional area and the velocity pressure that we need to calculate the volumetric flow rate. So here's our area, here's our velocity. Multiply those two together, there's our flow rate. Now we have what we need to calculate the capture velocity using the capture velocity formula. So plug in our flow rate. 10 is a constant. We've calculated our area already, 0.196. The distance from the hood in feet, 5 divided by 12 is 0.42 feet. 5 inches divided by 12 inches, that gives us our distance in feet, 0.42. Do the calculations in the denominator, we end up with 3.724. Divide 1106.82 by the 3.724. The capture velocity that we need to efficiently capture the contaminant is 297.2 feet per minute. Now remember, capture velocity is different than this velocity. This is velocity flowing through the system. This is the velocity that we need at the inlet to suck in the contaminant that we're trying to capture. All right, this, maybe I went too fast, but it's not a hard problem as long as you get the steps in order. Again, start with the formula that we're using to calculate the answer and then work your way backwards. Again, we didn't have the flow rate given to us, so we had to calculate the flow rate. To calculate the flow rate, we had to calculate velocity and velocity pressure. Or to get velocity, we had to have velocity pressure. Then once we had everything we needed here, along with the area, we have the flow rate, plug it in, and we're good to go. Right, let me know if you have any questions. If you're watching this video and you're lost, let me know. One thing good about videos, you can pause it and replay it. You could even do the slow motion thing if I was going too fast. All right, another type of calculation that you might see on the CSP exam is calculating the capture distance when you already know the capture velocity of the system. You know the capture velocity is 469 or 100 feet per minute. How far away from your inlet can the source be for that system to effectively capture the contaminant? And here's a problem like you might see. Capture velocity in a local exhaust ventilation duct is 100 feet per minute, and the airflow rate is 469 cubic feet per minute. To capture the contaminant, what is the maximum distance between the inlet and the contaminant source? The duct is round with a diameter of 8 inches. And here's the formula that you're going to need. This is the basic capture velocity formula, but we're not solving for capture velocity. That's already given to us. We are solving for x, which is distance between the source and the inlet. The equations that you see here are equivalent. The equation below is a transposition of the original equation set up to solve for x. On the ASP or the CSP exam, if you see a problem like this, they're not going to give you this formula. You'll either have to remember this formula or be able to do the transposition. And on the next slide, the last slide we're going to look at in this video, I'll walk you through the process of transposing this formula into this formula so that you can solve for distance. But let's go ahead and solve this. Back to this question here. Again, we have to have cross-sectional area of the duct to calculate the distance that we're shooting for. Again, we're shooting for distance, and when we run through the area calculations, we end up with a cross-sectional area of 0.371 square feet. Once we have that, we can plug into this beautifully transposed equation and do the math. Again, Q is 469. Our area is 0.317. Our capture velocity is already given to us at 100. Velocity, again, that goes in the numerator and the denominator in this term. And then our constant is 10. Now we just do the calculations, and we end up finding that we need to be within at least about 8 inches for this system to be effective at this flow rate and at this capture velocity. The hood needs to be 8 inches or less from the point where the contaminant is being generated. Right. Again, if you have any questions about the math involved here, let me know. When it's all transposed for you, it's a pretty easy problem. Like I said before, if you get into this on an exam, you'll be given this formula. You'll have to do the transposition. And here is the process for transposing. If you can't memorize the formula, here's how you would transpose it. Again, here's the formula. We want to solve for x. Multiply both sides by 10x squared plus a. When we do that, we end up with v 10x squared plus av equals q. We subtract both sides by the term a times v. When we do that, we lose it on this side and it's transferred over to this side. And that's what we end up with. Now we need to divide both sides by V10, by the term V10. When we divide both sides by V10, it disappears, it's canceled out over here, and at this iteration, this is what our calculation looks like. We end up with x squared equals q minus a times v divided by v times 10. And you can probably guess what the next step is. Take the square root of both sides. We take the square root of x squared, that becomes x. We end up with x equals the square root of q minus a times v divided by v times 10. I'm going to go back through that again with you. Just make sure. See if I can get rid of my, whoops. That's not what I wanted. There we go. Start with a clean slide here. Okay, again, we have a problem where we need to solve for distance, and we're given this formula. We need to transpose it. We want to solve for x. The first step to transpose this and solving for x is multiplying both sides of the formula by 10x squared plus a. When we do that, 10x squared plus a cancels on this side, and you end up with v times 10x squared plus a. I kind of left that out before. That v times 10x squared plus a becomes v times 10x squared plus a times v equals q. Yeah, we're still trying to isolate the x squared. That's what we're going for here. We need to get all of the rest of these terms over on the other side of the equal sign. We'll start with a times v. We can move it if we subtract both sides. If we subtract a times v from both sides, and we end up with v times 10x x squared equals q minus AV. Now we need to do something with the V10. Again, we're trying to get x isolated. Divide both sides by V10. When we do that, it cancels on the left, and we end up with our equation looking like this. We're almost there. We've got it isolated down to x squared, but we want x, not x squared. To get rid of the squared, we take the square root of both sides of the equation. When we take the square root of both sides of the equation, this is what we're left with. X equals the square root of q minus AV divided by V10. All right, hey, if anybody would like more practice with this, if you have more questions, I know math may not be your strong suit, and that's fine. You can be a successful safety professional without having excellent math skills. But if I can help you, let me know. If you would like some more practice problems, or if you'd like to sit down and work through some problems together, just let me know, and we can do that. But that's it for this video. And hopefully you have a better understanding of the methods used to calculate capture velocity. All right, I will see you in class.